You ever stop and think about what's actually happening when you click on a link? I mean, it feels totally instant, right? But in that tiny fraction of a second, a little piece of data, what we call a packet, kicks off this wild journey across the entire planet and back. So in this explainer, we're going to follow that single packet, step by step, to see how the internet really works. Okay, let's get into it.
So here's the plan. We're going to break this trip down into 5 key stages. We'll start right here, inside your own local network. Then we'll see how it connects to the internet. After that, it's a race across the global data superhighway. We'll find out how it finds its destination using the internet's address book, and finally, we'll follow it on its journey all the way back home to your screen.
All right, so every story has a beginning, and for our data packet, that story starts right at home. Before it can even think about traveling the world, it first has to figure out its way around the network inside your house, or your school, or your office. This is its very first step. Okay, so you click. Bam. What happens in that very first microsecond? Your computer immediately sends out a request. But where does it go? It doesn't just magically teleport onto the internet. No. First, it has to talk to the other devices that are right there in the room with you. This little neighborhood is called a local area network, or a LAN for short. The best way to think about it is like a private digital club. It's what connects all the devices in one building. It's all privately owned, and because all the devices are so close together, the data can move around incredibly fast.
And this slide just puts it all into perspective, right? On one side, you have your LAN. It's small, it's private, it's super fast. And on the other, you've got the wide area network, or WAN, which is basically the internet. It's the complete opposite. It's huge, it's public, and the data rates are comparatively a lot slower. Our little packet has to bridge that massive gap. Now, to make all this local magic happen, you've got a whole team of hardware working together. Your device has a network interface card, or NIC, that gives it a unique physical address. Then there's the switch, which acts like a local traffic cup, telling all the data where to go. You might have servers for things like file sharing, and of course, you've got the cables, the actual physical roads for all that data to travel on.
Okay, so our data packet has successfully navigated the local scene. Now for the really exciting part. It's time to leave home and get out onto the open internet.
And this is where the router steps in. The router is the hero of this part of the story. Its main job is to connect 2 different networks, in our case, your private LAN and the public WAN. It's basically the front door, the gateway to the rest of the internet. And, super importantly, it does this kind of translation service, which we're going to talk more about in a bit.
Now, often working with the router is a modem, and this device is a totally different kind of translator. So your computer thinks in digital signals, just ones and zeros. But a lot of the internet infrastructure, like old phone lines, uses analog waves. The modem's job is to modulate that digital signal into an analog one to send it out, and then demodulate any incoming analog signals back into digital. And that's actually where it gets its name, modem.
And just like that, our packet is out the door. It's on the open road. And this isn't just any road. This is a global superhighway on a scale that's almost impossible to imagine, made of actual wires, beams of light, and radio waves.
So what is the internet really? Well, at its heart, it's a massive network of other networks. It's not just one thing. It's a huge collection of countless different networks that have all agreed to speak the same language, a set of rules called the TCP/IP protocol. And your ticket to get on this global network? That comes from your Internet Service Provider, or ISP. And this table is awesome because it shows the physical reality of that network. The data travels through all kinds of different media, and each one has its pros and cons. You've got your traditional copper cables, which are cheap but can get interference. You've got fiber optic cables, which give you incredible bandwidth and security but are expensive. And then you have wireless stuff like radio waves, which are great for long distances but can have issues with interference. Our packet might actually travel on all 3 of these in just one trip.
Okay, our packet is now flying across this global network at pretty much the speed of light. But the internet is huge. How in the world does it know where it's going? It needs an address.
I mean, seriously, think about it. There are billions of devices connected to the internet. Sending a piece of data to the right one is like trying to deliver a letter to a specific person in a world with billions of houses and absolutely no street signs. So how does it work?
Well, it all starts with something called the Domain Name Service, or DNS. You could literally think of it as the internet's phone book. When you type a name that humans can read, like znotes.org, into your browser, your computer has no idea what that actually is. So it sends a request to a DNS server, which looks up that name in its huge database and sends back the real, machine-readable address, the IP address.
And this is that IP address. For decades, we used the 32-bit system, IPv4, but we were literally running out of addresses. The solution is IPv6, which uses a 128-bit address. The difference in scale is just staggering. There are more possible IPv6 addresses than there are atoms on the surface of the Earth. This is absolutely essential for the future, especially with the Internet of Things, where billions of new devices, from your watch to your fridge, are all going to need their own unique address.
Okay, now remember that translation thing I said the router does? Well, this is it. Your computer on your homeland has a private IP address that's only unique inside your home. Your router, on the other hand, gets a public IP address from your ISP, and that one is unique across the entire Internet. The router uses a clever process called Network Address Translation, or NAT, to let all your devices share that one public address. Here's the key takeaway. Your computer isn't directly on the Internet. Your router is.
All right, mission accomplished. Our packet, guided by DNS and its IP address, has reached the destination server. That server processes the request and then sends a new packet, this one containing the web page or video you actually wanted, on the return trip. It's time to bring the info home.
Now for stuff like video, the data comes back to you using bit streaming. This is just a continuous flow of those digital signals, the ones and zeros, sent at super high speed. It only works if you have a fast connection and a clever little trick using something called buffers, which are just small, temporary storage areas.
And you experience this in two main ways every single day. First, there's real-time streaming, like watching a live football match. It's broadcast as it happens, so you can't pause it. Then there's on-demand streaming, which is like watching this explainer right now. You're requesting a file that's already on a server, so that buffer could fill up and let you pause, rewind, and fast-forward all you want. And this is the whole reason your internet speed is so critical for a good experience. With streaming, you're literally downloading and watching at the exact same time. Your connection has to be fast enough to fill up that buffer faster than you're watching the video. If it can't keep up, the video stops, and that's the dreaded buffering screen we all hate. So there you have it, from a simple click on your local network, through routers and modems, across a global web of cables and waves, guided by these massive address books, and streamed right back to your screen, all in the blink of an eye. This whole system relies on everything from your local switch to global servers, so it makes you wonder, what's the weakest link in this incredible chain? Is it the physical cables lying on the ocean floor, the complex logic inside a router, or is it the trust we have to place in some random server to tell us the right address?